Okay, welcome again to the afternoon session. We have now Dr. Anton Timur Jaelani, who will be speaking about introduction to gravitational lensing. Anton is one of our staff at ITB, Department of Astronomy, but he is now also a postdoctoral fellow at Kindai University in Japan from 2018 until now. He received his BSc and MSc from Department of Astronomy at ITB and his Doctor of Science at Astronomical Institute, Tohoku University, Japan. So let's welcome Anton.
Okay.
Start now.
Okay, thanks, Dr. Hesti, for introducing me. Yeah, let me share my screen. Hello, I hope you can see my screen well. So today I got a job to give you a lecture about the introduction to gravitational lensing, especially about strong lensing, because strong lensing is my research field and my concern. So this lecture also will be followed by introduction to weak gravitational lensing by Dr. Masamune Ogure from University of Tokyo. Now, my affiliation in ITB as a lecturer and also in Kindai University as a postdoctoral. Okay, let's start my presentation today. So if I will start my presentation by showing you this picture from Hubble Ultra Deep Field. So in this picture, we can see so many galaxies in one small patch from the sky. So if we try to pick some point, one point here, you will find also galaxy. So you can imagine that our universe is very large because, as you know, that our Milky Way as a galaxy also has a larger size. And then if we look at this figure, we can see that the galaxies in this figure also has a different orientation, different morphologies, and different colors. So it's most likely that the galaxies will have a random orientation also, random size and so on. But if we look at this figure, maybe we can see a spiral galaxy that also follow known physics. Maybe you have got a lecture from previous lecturers about what galaxies morphology, spiral, also elliptical. Some galaxy also irregular, but they still follow known physics on size and also in another manner. Okay, but if I show you this picture, maybe some of you will see something odd here. With slightly different with a previous figure, but yeah, I think that most of you still look this picture the same with a previous picture, you only see there is so many galaxies with different orientation, also with different morphologies. But if I have, if I give you a clue about what's strange in this picture, in this figure, uh, as you can see in the right panel, there is some galaxies from the background has been splitted by massive object in between us and the background source. So I will pick one of them. You can see in label A1, A1.1, A1.2, A1.3, A1.4. These galaxies, these four spiral galaxies come from one galaxy at the background. And a spectacular thing here that we still can see in this region, we can see spiral galaxy. Maybe we can say it has a small distortion, but maybe as your information first that this galaxy has been splitted by a Gravitational lensing effect. So if you look at this picture, this one, this one, this one, and this one is come from one galaxy at the background. Okay, it's okay. Maybe from this picture, it's quietly hard to make you amazed or to make you wonder that how beautiful or how amazing Gravitational lensing it is. Okay, now I will show you about spectacular phenomena from Gravitational lensing on the sky. So this one is one of spectacular images from Gravitational lensing. We call it as a smiley galaxy. So this smiley galaxies, maybe roughly you can see there is two bright red galaxy at the center. It looks like the eyes. And we can see there is a arc or tangential arc. At least we can see three and one here, the red arc. So this arc made face shape like something we know in the common in daily life. So this object named by this name, Kasawari 2, CSWA, and also from SDSS, Flown Data Sky Survey, code name, something like this. And these two galaxies, the red galaxies, located at a redshift 0.43, and the left source, this one is come from redshift 0.97, and this arc come from a redshift larger than 1.4. So if you, maybe some of you know something or feel that you have seen this particular feature in your daily life, or maybe in your when you watch a movie, I will show you. Yeah, this picture is similar like a cat figure from Alice in Wonderland. So yeah, let's imagine that this is similar with cat from Alice in Wonderland. So it's a beautiful feature that sky provide the sky has provided to us, for us. Okay, now the question is, what is the Gravitational? Okay, in this figure, I wanna give you a big idea about the Gravitational. Maybe in Dr. Hesti's lecture, she has given you explanation, general explanation about the Gravitational. So I will repeat in this slide. So Gravitational is will happen if we have this configuration, something like this. The observer, us on the Earth, there is a massive object in between Earth and background source at the distant source at the background. So in this case, we there is one spiral galaxy in a spiral or regular galaxy at the background. So because there is a massive object in between us and a distant source, so light from distant source should be follow the curvature of space-time. Because if we have a massive object in between us, the massive object will make a space-time curve. And then the curve space-time will tell photon how they move toward us, something like this. That's why we, at the previous figure, we see there is a splitting image by Gravitational. So in this figure, we can see there is an image here and there is image here. So this is a big idea of the Gravitational. Okay, I will give you another analogy of Gravitational. So this analogy comes from Philip Marshall, and this figure comes from Thomas Utter. So this analogy, you can do experiment in your home using a wine glass, something like this. If you have a wine glass, you will see there is a bottom in a wine glass, or something like I've shown you in this figure here. So if we want to see analogy of a Gravitational, we can use this bottom of a wine glass. Okay, by using a candle in front of us, and then we put bottom of a wine glass in between us and a candle, we can see images of fire from a candle, something like this. Also like this, and sometimes if we change the orientation of a glass, we can see different configuration of images. It's like a ring like, something like this. So if we look at the result from Gravitational on the sky, we can see similar feature, something like this. You can compare with left images. These images corresponds to represent a candle here. And if we have a galaxy, something like this, with particular orientation, we will see configuration of multiple images will be something like this. So it will similar. So yeah, you can do this such kind of experiment in your home to see if you have different angle respect to line of sight from our eyes to light source like a candle. You will see different images, something like this. Okay, that's one of the analogy uh, for gravitational lensing. Okay, now if we talk about the gravitational lensing, we will talk about gravity because we talk about the massive object. So one thing that I should tell you, if we want to study about gravitational lensing, most of gravitational lensing is all about general relativity. Why? Because we talk about um, curvature in a space-time. Okay, in this figure, I will show you there is a picture here. There is a Earth as an observer, the Earth as observer, and also one stars here. Okay, if there is a massive object in between us, okay, at uh, at the time when general relativity start to develop, maybe one of the massive object has known at the time is the sun. So if we have the sun in between us and the stars, so the light path from the stars will be deflected by a massive object like the sun here. So because this deflection angle, we will see the projection of the apparent stars or location of the stars will be changed due to this deflection. So we, from observation, we only see that the location of star will be here, not here. Okay. Okay. Let's back to general relativity. So if we talk about general relativity, we talk about one of topic in, no, I mean that this deflection angle is one of the consequences of the equivalence principle. What is the equivalence principle? Equivalence principle tell us about equivalence of a gravitational mass and inertial mass. Inertial mass. Yeah. In other way, we can take an analogy about if we have experience about if we close to a massive object, we will have experience that the massive object will attract us because of the gravity. But in other experience, we can say that it will be similar with the experience when we lie on the accelerated in accelerated rest of frame. So if you are in a rocket or something like this, you will get a more acceleration. So it will be similar with attraction from gravitation. Okay, that's equivalence principle said. Okay, from these equivalence principles, we can derive deflection angle due to massive object using general relativity. If we consider for a point mass, we can write down the deflection angle or alpha here, something like this. Because we consider the sun, we can use m dot as the solar mass and r dot as solar radius. So we can get the deflection angle from this. If we say that deflection angle only can be calculated by general relativity, it's not true, because if we calculate with Newtonian, also we can get the deflection angle, but the value of the deflection angle from the Newtonian will be half of value from general relativity. That's why this value need to be confirmed by observation. But it's not so easy task to confirm this deflection angle using observation at the time. Okay, but luckily that some people at the time has a brilliant idea to observe deflection angle by using a particular event like a solar eclipse. Why they use a solar eclipse? Because when a solar eclipse happens, we can see that the sky at the time will be dark enough so we can see the background star behind the sun. Okay, this observation of the solar eclipse has been done by Eddington and their colleague. They took to the same coordinate but at the different time. So one time when a solar eclipse happened, and they try to observe the same coordinates of sky coordinates next month later. So the idea is when we can observe the two coordinate on the sky. No, I mean that the same coordinate on the sky from sky coordinate. We at the different time we expect that there is some deflection if our theory of gravity is true. There will be there is a changes in the position of the stars. So this one is from BBC documentary. We can see there is the stars have some changes in their position here. So after that, they try to calculate how large the deflection angle by the sun. So when they try to when they tried to calculate the deflection angle, they found that the value of the deflection angle close to general relativity prediction than Newtonian. So from the result, Albert Einstein became a really bright star at the time. So after that, Einstein tried to calculate another deflection by another stars, but from his calculation, he found that the deflection angle is extremely small. So it will be hopeless to expect we can observe another gravitational lensing effect from another star. Then 20 years ago, 20 years later, Fritz Zwicky tried to propose nebulae as gravitational lenses. Nebulae, maybe at the time they call it a nebulae, but from now, from uh, the recent knowledge, we know that that particular object as galaxies. So Zwicky tried to propose if we have another massive object like a galaxies or like a nebula at the time, uh, it will be give us give it will be it will give us a new hope to observe gravitational lensing. But from this proposal from Zuki, we need to wait until 30 years later to find the first double quasar, KSO 0957. It's very famous lensing quasars, as also as known as twin quasars. So 30 years later after Fritz Zwicky's proposal, we can see the first double quasar, something like this. The question is, how do we know? How did we know that this object come from gravitational lensing effect? So thanks to spectroscopic information that we can confirm that this object, the blue one here and the other blue here, come from the same object at the background. Because from observation, spectroscopic observation, we can see a similar feature from these two objects, and they located at high redshifts. So another clue is in between these two objects, we will find there is one red galaxy. And this red galaxy has a smaller redshift than these two object. So this how we confirm gravitational lensing by spectroscopic observation. Okay. Okay, now we are going to discuss about the mathematical side in gravitational lensing. So gravitational lensing is quite simple because we only we only learn about the general relativity, quote unquote, only learn general relativity. And if we try to build that scheme for to see how geometry of a gravitational lensing is quite simple. Okay, I will show you in this slide. Okay, if we have a blue dot as observer, let's say the Earth here, and we have another object as lens, the black circular here, and we have two source in this location. Okay, if there is no lens object in between us and source, the light path from this source will directly come to us, following this blue line here. But if there is a massive object in between us and this source, we will see a photon from toward this direction will be deflected by this massive object. So the photon's path will be something like this, follow this thick black line here. Okay, so if we take the projection, we will see that the stars or the background source will be located in this position, something like this. Okay, so in this picture, I have to mention about alpha head as true deflection angle, and beta is angle of true position, and theta angle for image, and alpha, this alpha is a scaled deflection angle, and psi is impact factor for lens. And I need to mention about one reference, we call it as a line of sight. So line of sight is an imaginary line that connect us as observer to center of the lens, something like this. Okay, so this three angle will be defined respect to this line of sight, something like this. And then we also have another parameter, measurable parameters come from distance. So we will have three distance here. At least the first one is DD, distance from us to lens, DDS, lens to source, and DS from us to source. So this, okay, I have to mention also that this parameter distance is from measurement, that from spectroscopy we can get redshift, and from redshift we can calculate the distance. Maybe you can see again, can remember a lecture from Dr. Pramana about the cosmological distance. Okay, from observation, we only can, for angle, we can observe only this theta, because we cannot see the true source, intrinsic source, and intrinsic location. I mean, the true location we cannot observe, so we only observe this one. Okay, so this one will come from models and so on. So from this, okay, I need to mention also, if we need to define this this plan. We call it lens plan, and for this one a source plan. So from this simple trigonometry relation, we can derive the lens equation. This one, the top equation, we call it as lens equations. So the angle of true location of source relate to this angle of image minus scaled deflection angle. So we also have another relation to define that scaled deflection angle will be proportional with true deflection angle times distance ratio, something like this. Okay, so it's quite simple. And then since we have a relation of scaled deflection angle, something like this, we try to calculate about the deflection angle due to gravity from mass. So in this another diagram, another scheme, I will show you that I have mentioned this one. If we have, at least we have two plan. The first one is located in lens. We call it as lens plan. And for this one, we call it a source line. So we have to take a good assumption if we want to start to calculate about the deflection angle. What is the good assumption that we can use? Okay, if we look at this configuration, we can see that there is a cosmological distance. If we talk about the cosmological distance, we talk about a very large mass. No, about the distance, I'm sorry. If we talk about the distance, we talk about a very large distance. So if we compare with the size of the lens object, we can say that the size will be quite extremely small compared to distance. So if we can say that the size is quite small, so we can take thin mass approximation from our calculation. So if we take that assumption, we can derive or write down the deflection angle equation, something like this. So in this one, we call it as a surface mass density. And this part is about a small area that we calculate in this lens plan. And this one comes from general relativity. Okay, so, but the problem is it's quite complicated, complex if we calculate deflection angle from this form. So we need to make we need to take another borrow another parameter to make it more simple. So as you see in the previous relation, geometrical relation, we have many relations, something like psi. We can have a relation with this theta and also dd. And we also have another relation of, we can take another relation from this picture. So if we have a scaled deflection angle, we can put here to, and so this distance ratio will be put here. And also because we have psi relation, we can put another relation which has theta here. And this one is another form for a scaled deflection angle from this one and this one. Okay. So in this form, we can see that we have theta, and we have theta, and we have distance. So distance is measurable parameter, and theta also we can get from observation. Okay. Okay, this one, the original form of a deflection angle. So after we got this another form, we try to change this a little bit by using, we move this, what's this, this distance ratio inside integral here, and we will find something like this. So if we look at this part, we can see, we can define another parameter to make it our life simple. So we can define kappa, that kappa, we call it as convergence, defined as surface mass density divided by is divided by critical surface mass density. The critical surface mass density will be defined as this equation. So we can see this part is constant, and this part is a ratio from measurable measurement distance. So we can get this one to characterize how the power of gravitational lensing. So this kappa is represent the power of gravitational lensing. So kappa larger than 1, we will see strong lensing effect. If kappa quite small, we only see the small distortion. So that's topic we'll discuss further in quick gravitational lensing. Okay, then the problem is it's quite hard if we talk in this form only. So we need to define another parameter that we call it as lensing potential. So this is the lensing potential. You can see here. So with some calculus manipulation, so we can took a relation between lensing potential and deflection angle. So you can try in your home that this relation will be this two parameter lensing potential and what is deflection angle has a relation, something like this. Yeah, it's quite easy, so you can try in your home. So we can say that the deflection angle is derivative of lensing potential, something like this. So if we took another derivation, so we will got this form. So maybe some of you is familiar with this form. This form is come from Poisson equations. Okay. Okay. Now we have discussed about mathematical side in gravitational lensing. So let's understand what we have just written before. Suppose we see multiple images come from the same source at the background. So by using a scaled deflection angle, and then we have a lens equation, we can constrain the projected mass surface mass density. Okay, this one is example of a strong gravitational lensing. You can see that there is a massive galaxy at the center, and there is a blue arc. That this arcs come from a distant source. Okay, now in this slide, I need to tell you that if we have, okay, let's back to this figure. So in this slide, if you can see that this configuration, so observer, lens, and source doesn't located at the on the line of sight. But if there is a particular case or a special case, maybe we will see at some figure in some image, we can see a circular or ring like from Einstein ring. So it's most probably that this source located in on the line of sight here. So if we have that particular event, we can see that multiple images formed by gravitational lensing, which is formed by gravitational lensing, will has this such kind of feature ring-like. So if we have ring-like something like this, it's more easier for us to calculate the power of gravitational lensing, or how large the massive object in between us and distant object. So we can define Einstein radii, that's Einstein radius. So this Einstein radius will be has a relation with a mass, something like this. This one measurable distance can measure using redshift, and this one is constant. So we can see like a linear relation between Einstein radius and mass. So this Einstein radius as indicator for the size of a lens, something like that. Okay. Okay, now we have discussed about deflection angle, so it will be changed in position. But if there are any effect from like, how should I say, from photometric observation, yeah, there is a another effect from gravitational lensing. We call it as magnification. So sometimes we can see object is very bright. Sometimes maybe in another since gravitational lensing will strong gravitational lensing will make a distance source split it into multiple images. Sometimes in one image we can see it's very bright, but another images we will see it's quite faint. So that come from magnification effect of gravitational lensing. So if we talk about a gravitational lens or a lens equation, we talk about the mapping. So one source will, because split it into multiple images, we talk about the mapping from one to many images. Okay, so the magnification of each image is given by the Jacobian of transformation equations, something like this. What is the basic idea of the magnification? Magnification tell us about the ratio of cross section in source plane and also in compared to cross section in lens plane. So there is an important note here. I have to remark that lensing doesn't produce new light, but lensing only change the cross section. So if we consider that surface brightness conservation, if we say that surface brightness is conserved, so if cross section has been changed due to gravitational lensing, so we can see that effect of magnification there. So this one, the question Jacobian transformations. So as you know that beta has two direction into coordinates, and also theta also into coordinates. So beta 1, beta 2, theta 1, theta 2. So in this form, we will have a matrix, magnification matrix 2 times 2. Okay, let's move to this equation. So if you remember, this equation just a lens equation, but in different form. So if we took a partial derivative of this beta respect to partial derivative to theta, we will have a lens equation something like this. Okay, so since alpha also has a relation with what should I say, lens potential, we will have this form. Okay, so from this form we can write down this one inverse of A here. So we can define another parameter. The first one kappa, we call it before kappa in different form, something like this, and another one is gamma. So what is the meaning of a kappa and gamma here? So kappa and gamma, if we split, these equations into this equation, we can split into two parameters, something like this. The first one only depend on kappa, and second ones depend on gamma. So kappa means I can give you illustration of what is the meaning of kappa. So the meaning of kappa is how gravitational lensing change the cross section isotropically, something like this. So kappa will make a circular bigger or smaller. That's kappa means. And if we talk about gamma, we talk about its distortion. So sometimes we will see the circular will be changed their shape, more elongated, something like this, has a like a elliptical shape, something like this is due to gamma. Okay, so this what's this inverse of A here will change from circular if there is kappa larger. Okay, if there is a kappa, this circle will change isotropically, something like this. If they have gamma, they will be more elongated than this one. Okay. So this one distortion, and this one is change the isotropically. Okay. Now, another parameter that we have to discuss in this gravitational lensing is about the Fermat potential. So Fermat potentials, we can write down something like this. Here there is two components. The first one is come from geometry, and the second ones come from potential. It's come from gravity. So this one come from geometry, because if we have multiple images, each images will the light of two images will have different paths when they propagate from distant source to us. Will have a different path, and it means that they will have different distance, something like no, different distance, different length. Okay, and then if we talk about gravity, since the position respect to the center of a lens will be different for two images, they will feel different potential in different position. So if they closer to lens, they will be so down much than another images that farther from lens center, something like that. Okay, and then if we try to derive this the Fermat potential, and our derivation equal to 0, that we will find that this derivative will back to our lens equation, something like this. Okay, what does it mean? It means that about if there is gravitational lensing effect, they will arrive to us at the a certain position. What is the certain position means? So if there is no lensing here, the distant source will be propagate light from distant source will be propagate to us directly in a minimum here. But if we have a massive object in between us and distant source, there is another choices to light to come to us. So they will arrive uh, uh, in minimum or saddle point or in maximum. So if more complex massive object, we will have another point, another minimum, or another saddle point, something like this. So this call it a Fermat principle. So if we talk about this one, we talk about the Lansing equations. So that's why if we look at the Gravitational Lansing image, we will see why they should be in that location. So it will be related to Fermat's principle, something like this. Okay, now about the time delay. Okay, I need to mention that the time delay, because if we talk about the multiple images, we talk that there is a geometrical component and also a potential component. So the one image, and if we compare one image and another image, we will have a different length. And will have different potential when they try to propagate from a distant source to us. So if we compare one image and another image, we will find that there is a delay between two images. So the delay is come from these equations. We can call it as this equation. So these equations tell us about this one depends on cosmology. So we can constrain the H naught using these relations. And also these ones come from potential. So it will depend on lens mass distribution. This one come from model, lens mass model. Okay. Then consequence of magnification is caustic. So we will have, if we have a determinant of A equal to 0 in the image plane, we call it as critical curves corresponding this situation in a source plane, you call it as caustic. So this one is caustic and this one critical curve. So if we have an object here in a source plane, we will see one image in a lens plane. But if we move our object here, we will have three multiple images. If we move at the center, we will have more images of 5. So we can see that from outer to inner region, we will have images plus 2, 1, 3, 5. But also it will be depend on your mass complication. So if your mass is cluster galaxy or your mass has substructure, it will be different case. Okay, I want to show you if we have a different location and different path of different location in a critical in source plane in caustic will be make a different multiple images configuration, something like this. If red here will be corresponds to this one quadruple image. Green will be something like this. We have our elongated image, something like this. And if we look at the purple, pink here, so we'll see small distortion, and there is a very faint counter image at the center here. But from observation, we cannot see this one, but we only see this small distortion here. So for different configuration, we can see different, for different location of the source will be give us different configuration, something like this. Okay, now if we talk about lensing, we sometimes we no, in general we can say different form. Strong lensing, we can see very huge angle elongated arc, something like this with counter image. So strong lensing talk about very elongated arc and also multiple images. But if we talk about weak gravitational lensing, okay, you can see this lecture on the Friday by algorithm. With gravitational lensing talk about small distortion in the universe. Then for microlensing, I will give you animation for this microlensing. Okay, so since this summer school talk about dark matter, so since we don't know what the dark matter from what dark matter made of, so we only can constrain from lensing, we can constrain about density and also about the total mass in the universe. So yeah, this is the unique way to learn about mass mapping in the universe, since we cannot observe dark matter in electromagnetic wavelength. So yeah, since dark matter only has interaction by gravity, so gravitational lensing is a unique way to learn about this one. Okay. Also, as you see before that, from time delay, we can constrain cosmology, because if you look at the lensing equation, you can see there is a distance ratio. So distance ratio, as you know, that distance depends on cosmology. So if we can use a lensing as a cosmological constraint, we can constrain cosmological parameter, something like this, or also we can consider about concentration of structure in the universe to see or to check whether our prediction from theory is true or not compared to observation. Okay, this one is one example about cosmological constraint from lensing. Okay, another one is since we also can constrain a cosmological parameter, we also can test another cosmological model using this lensing. Okay, of course, we need to compare with another observation like a CMB or something like this. Okay, and also in lensing, since lensing is a rare phenomena in the universe, but in the rare phenomena, we also has the rare phenomena in lensing. We call it as double source plane. So from my previous discussion, we only discuss about one source plane, but sometimes we also, no, bukan, not sometimes, but in general, because we have many structure in between us in and distant object, it's very most likely that they will deflect the source, the light from the background source will be deflected by several times because there is so many layer of mass. But we cannot see or we cannot be separate from observation. So we need to make a model to separate it. But if we have a particular case, something like this, to source, we can see there is there are two arcs that come from different ledgers, something like this. This object has been observed by Tanaka et al. 2016. This one, my colleague from Naoji. So if we can observe such kind of this object, we will by single object, something like this, we can constrain the cosmological parameters like we have done in this result. Okay, so yeah, lensing also can give us a hint about the distribution of dark matter. If we talk about a strong lensing, we talk about the inner part. Let's say this one is cluster, so we can constrain the mass distribution in the inner part using strong lensing. But if we combine with lensing, maybe I mean that if we combine with lensing, we can constrain the mass distribution at the larger radii. So if we look at this result, that we can compare since we can measure mass from luminous object at the center, we can compare with the total mass come from strong lensing. So something like this. Okay, now this Hubble tension has been discussed in Joel public lecture before. So I want to highlight that one of these results come from strong lensing. So it's come from time delay analysis using this 6 quasar lens quasar by Holy Cow team. So you can see that the Holy Cow team result in this green dot here. It's quietly with small error here compared to result from the early universe from Planck and the DES. So we can see there is a tension. So I need to highlight that lensing also good tools, astrophysical tool to measure cosmological constant, especially H0 here. Okay, so I want to show you how to measure time delay from observation. If we time delay, of course, we cannot observe time delay if our source is a common galaxy. But if we have, if the source has a variability, we can see from that variability, the variability will be shifted due to geometrical component and also due to potential component in Fermat potential. So this is the illustration in animation here. You can see this feature here, like there is from flat feature to the flux increasing here. So in another feature, in other images, we will see also similar feature, but shifted by time here. So if we compare one image to another image, we will get how long the delay from this between this object and between this image and this image, something like that. Okay. So if we want to measure this such kind of time delay, we need to observe or do monitoring with long time, something like this. It's about 239 days to make a plot, something like this. Okay, this one illustration of microlensing. So microlensing something like this. If we have moving object in between us and the stars, we will see that the brightness of the star will change due to gravitational lensing. So if the moving object is only one, like stars, we will only see one bump, something like this. But if we have another companion object, on this moving object, we will see another bump. So this another bump is clue that the moving object has another companion. So this method can use to detect exoplanet. Okay, also from microlensing we can map another compact object, because some compact object they have faint light. So by observationally, we cannot. It's very difficult to detect by common observation. So we need such kind of method from microlensing to map compact object like dwarf or faint stars and so on. Okay, this one is we can detect stars from a distant object using microlensing. So you can see in Kelly's paper about lens stars magnified by 2000. So it's very huge magnifications. And then this one is still about microlensing. And then we can build a microlensing map. So if we can see a map from microlensing, we can guess how many objects in between us and the source. I mean that compact object. Okay, microlensing also can consider to detect massive object like a black hole using yes, microlensing. Okay, this is also about quasar microlensing. So if we have quasar with variability, and we have, because we have in our galaxy most likely there is so many stars. So stars will give us also caustic, something like this. If we combine many caustic from compact object, we will see more complex caustic, something like this. If we have a background source, that the background source will be magnified by this caustic. Okay, so I also want to show you that this one, the result from our work, from our group. So now there is so many galaxy surveys, and from galaxy surveys we can search so many new gravitational lensing system. So since we will have many gravitational lensing system, we will do many science. So please stay tuned. So if you are interested in particular science by using strong lensing, you can contact me later. Okay, and this one is a good recommendation book review. if you wanna study about Gravitational further, you can read these books and also some paper review from these guys. Okay, thank you.